This is our second video lecture for Chapter 15, Acids and Bases, and we'll begin discussing how do we describe these acids and base systems and how do we quantify the acidity or the basicity of those systems. Now in the previous set of lectures we discussed the amphoteric nature of water. Water is actually an extremely weak electrolyte. Therefore there must be a few ions present. About 1 out of every 10 million water molecules form ions through a process called autoionization. So we can either write this as H2O going to form H plus and OH minus, or we can write this as two water molecules reacting to form the hydronium ion, the H3O plus, and the hydroxide ion. All aqueous solutions contain both the hydronium and the hydroxide ions. The concentration of the hydronium and hydroxide ions are equal in water. And when they're equal to each other, they both have a concentration of 10 to the minus 7th at 25 degrees C. The product of the hydronium ions and the hydroxide ion concentrations is always the same number. And this number is called the ion product of water and has the symbol Kw. So thinking back to that previous reaction where we have the two waters combining to make the hydronium ion and the hydroxide, if we were to write the equilibrium constant for that reaction, the mass action equation, we take the concentration of the hydronium ion, so the H3O plus, and multiply it by the concentration of the OH minus. But notice that water is our reactants and those are in the pure form, so that doesn't show up in our K expression, our mass action equation. And to indicate that this is the equilibrium reaction associated with water ionizing it, we have a special subscript for this case. This is the Kw. Now the Kw is 1 times 10 to the minus 14th at 25 degrees C. And when you need this for your exams or quizzes, this will be given to you. Now if you measure one of these concentrations, you can calculate the other since the concentrations are related to the Kw, since the product of the H3O plus times the hydroxide concentration always equals the Kw. Now because of this relationship, as the hydronium ion concentration, the hydroxide ion must decrease for the product to stay constant. So this tells us that these two concentrations are inversely proportional to each other. Now again, we said that all aqueous solutions contain both hydronium and hydroxide ions. Neutral solutions have equal concentrations of these two ions, the hydronium and the hydroxide. But acidic solutions have a larger hydronium ion concentration than the hydroxide. So the H3O plus concentration is going to be greater than that 10 to the negative 7th, and that means the hydroxide therefore has to be lower, so it's going to be less than the 10 to the minus 7th. And conversely, the basic solutions have a larger hydroxide concentrations than the hydronium. So the hydronium is going to be less than the 10 to the minus 7th, and the hydroxide is going to be greater than 10 to the minus 7th. Let's look at this example problem where they've asked us to calculate the hydroxide concentration at 25 degrees Celsius when the concentration on the hydronium is given as 1.5 times 10 to the minus 9th molar. And they want us to determine if the solution is acidic, basic, or neutral. So they've given us the hydronium concentration, and we need to find the hydroxide concentration. Now there's a relationship between the hydroxide concentration and the hydronium concentration using the ionization product of water. So the Kw equals the hydronium concentration times the hydroxide concentration. So if we know the hydronium concentration, which they've given us, the Kw is a known value that we can look up. We can solve for the hydroxide concentration. So we simply take the Kw and divide it by the H plus concentration. Then if we plug in those values, this is the 1 times 10 to the minus 14th value for the Kw, and the 1.5 times 10 to the 9th is the concentration of the H plus. We put this in our calculator and we get a value of 6.7 times 10 to the minus 6 molar. And because the hydronium concentration, which is 1.5 times 10 to the minus 9th, is less than the 6.7 times 10 to the minus 6, This means that the concentration is basic since the hydroxide concentration is larger than the hydronium concentration. Now this table is nice. It just kind of helps give you a pictorial view and the inverse relationship between the hydronium ion concentration and the hydroxide concentration. Now, even though it may look like it, neither the hydronium nor the hydroxide concentration will ever be zero. The sizes of the H plus and OH are not to scale. This is because the divisions are powers of 10 rather than units. Rather than just increasing 1 or 2 or 3, this is increasing in size of 10 to the 1, 10 to the second power. So there's a logarithmic relationship between these. And because it's easier to think about these in terms of logs, this is why we use the pH to report the acidity of a solution. So the acidity or basicity of a solution is often expressed as pH because it's much easier to report a pH of, say, 7 or 8 than looking at all those small numbers with the exponents. So a pH is equal to the negative log of the hydronium concentration. And if you need to find the hydronium concentration is equal to 10 raised to the negative pH. So this is the way to get the hydronium concentration if you're given the pH. But if you're given the hydronium concentration, you take the negative log of it to get the pH. And the exponent that we're using on is base 10. So the pH of water, where the hydronium concentration is 10 to the minus 7th, for neutral water or pure water, it's negative log times the 10 to the minus 7th, so the pH of water is 7. So we need to know the hydronium concentration to find pH. Now also too, while we're mentioning this here, the P of the pH, P simply means to take the negative log. We will be using several other P terms like pKa, pOH, pKb, and each time the P means the exact same thing. It means to take the negative log of something. So in this case, the pH is to take, and the pH simply means to take the negative log of the H plus concentration. And if the pH is less than 7, the solution is considered to be acidic. If the pH is greater than 7, it's considered to be basic. And if the pH is at 7, it's considered to be neutral. So I'm going to take a little bit of time to discuss significant figures and logs. When you take the log of a number written in scientific notation, the digits before the decimal place come from the exponent on 10, and the digits after the decimal point come from the decimal part of the number. So if we're looking at this here, we're looking at taking the log of 2.0 times 10 to the 6th. And that is the same thing as saying log of 10 to the 6th plus log of 2.0. When we do this calculation, we get 6.3030. Now notice that in our calculation, our number that we're taking the log of has two significant figures. The significant figures come after the decimal place. So since part of the scientific notation number that determines the significant figures is the decimal part, the sig figs are the digits after the decimal point in the log. So if we round this to the appropriate sig figs, the answer should be 6.30. So this number actually has two sig figs rather than three significant figures. The lower the pH, the more acidic the solution. The higher the pH, the more basic the solution is. 1 pH unit corresponds to a factor of 10 difference in acidity because of that logarithmic scale. Normal range for pH is 0 to 14. pH of 0 is H plus equals 1 molar. pH of 14 is hydroxide concentration equal 1 molar. pH can be negative, which means it's very acidic, or larger than 14, which is very alkaline. So you can have things outside the typical 0 to 14 scale. It's just that normal is 0 to 14. In this example problem, they want us to calculate the pH at 25 degrees when the hydroxide concentration equals 1.3 times 10 to the minus second molar. And they want us to determine if the solution is acidic, basic, or neutral. So we're given the hydroxide concentration. and they want us to find the pH. Well, if I have the hydroxide concentration, I can convert that hydroxide concentration to the hydronium concentration using the kW of water. And then once I have the hydronium concentration, I can use the pH calculation to determine the pH. So for the first part, I'm going to use the kW to find the H plus concentration, and then I'm going to use the pH equals negative log of H plus to find the pH. So using the kW and the hydroxide concentration, I can determine that the H plus concentration is 7.7 times 10 to the minus 13th molar. Now that I have the hydronium concentration, I can take the negative log of that to get my pH. So I've determined that my pH is 12.11. And remember, the pH is unitless. So because the pH is greater than 7, this means that the solution is basic. Now pOH is just another way of expressing the acidity or basicity of a solution. And the pOH is the negative log of the OH. And if you have the OH concentration, or if you're given the pOH of a solution, you can find the OH concentration by taking 10 raised to the negative pOH. And if we're trying to find the pOH of pure water, that pOH is the negative log of the hydroxide concentration. And we said that pure water at 25 degrees C has a concentration of hydroxide of 10 raised to the minus 7th. So the pOH of water is 7. Now to find the pOH, we must know the OH concentration. Now because the pOH is the inverse of the pH, a pOH of less than 7 is basic, and the pOH of greater than 7 is acidic, and the pOH of 7 is neutral. So to help us understand the relationship between pH and pOH, let's discuss that a little bit more. The sum of the pH and the pOH of a solution is equal to 14 at 25 degrees C. So we can use the pOH to find the pH of a solution. So rather than using the hydronium concentration and the hydroxide concentration, the ionization constant, we can use the fact that the pH plus the pOH equals 14. Now let's see where this comes from. So we're starting off the autoionization constant for water, that equilibrium mass action equation. We're going to take the negative log of both sides. And then using our rules of logs, when we multiply these together, this is the same thing as adding them when we break them apart. So the negative log of the hydronium concentration plus the negative log of the OH. And of course, if we take the negative log of this number, we get 14. So the negative log of the hydronium concentration by definition is the pH, and the negative log of the OH concentration by definition is the pOH. So the pH plus the pOH equals 14, and that also equals the pKW of water. And remember, P just means take the negative log. So if you take the negative log of the KW, you get the pKW, which is 14. Now another way of expressing the strength of an acid or base is the pK, which is a negative log of the equilibrium constant. So if we're talking about an acid and its equilibrium constant, the pKa is the negative log of the Ka. And if you want the Ka and they've given you the pKa, you can take that number and raise it to take 10 raised to the negative pKa to get the Ka value. And the pKb is just simply the negative log of the equilibrium constant for a base. Now the stronger the acid, the smaller the pKa. So a larger Ka means a stronger acid. This is going to result in a smaller pKa due to the fact that the pKa is defined as the negative log of the Ka. So the larger the Ka, the smaller the pKa. Let's now discuss finding the pH of a strong acid. There are two sources of hydronium in an aqueous solution of a strong acid, the acid and the water. For the strong acid, the contribution of the water to the total hydronium concentration is negligible. This is because this shifts the Kw equilibrium to the left so far that the hydronium concentration of water is too small to be significant. This is except in very dilute solutions, and we're generally talking about less than 10 to the minus fourth molar. And for a monoprotic strong acid, the concentration of the hydronium ion is going to be equal to the concentration of the acid. For polyprotic acids, the other ionizations can generally be ignored. So for example, 0.1 molar HCl has a hydronium concentration of 0.1 molar, and if you take the negative log of that 0.1, you get a pH of 10. So another way to think about this is because the HCl is a strong acid, it completely dissociates. So this is a one-way reaction. If we start off with 0.1 molar, and this is our initial concentration, since this reaction goes completely to the right, our change is we're going to lose 0.1 moles to make 1 molar of the H plus 1 molar of the Cl minus. So at the ending concentration, you have no more HCl as one molecule. You have 1 molar H plus and 1 molar Cl minus. So this is why the concentration of the strong acid equals the concentration of the hydronium ion, because it completely dissociates. But finding the pH of a weak acid involves a little bit more math. There are two sources of hydronium in an aqueous solution of a weak acid. One of those sources is the acid and the other is the water. However, finding the hydronium ion is complicated by the fact that the acid only undergoes partial ionization. Calculating the hydronium concentration requires solving an equilibrium problem for the reaction that defines the acidity of the acid. So we have to write the balanced chemical equation that shows the equilibrium of the acid dissolved in water. So we're going to look at finding the pH of a 0.012 molar solution of nicotinic acid. So they give us the formula for nicotinic acid and they give us the Ka. Now anytime that they give you a Ka, that's telling you that that's a weak acid. You don't have to know if that's a strong or weak acid. If they give you a Ka, you automatically know that it's a weak acid. So the first thing that we need to do is we need to write the reaction for the acid with the water. Then we're going to set up our ice table. And when we set up our ice table, HA, I'm just going to abbreviate for our acid, and the A minus is the conjugate base form. So that would be the nicotinate ion and the hydronium ion that's formed. So initially we have 0.012 molar HA in solution. And the A minus concentration, we haven't added anything else to it, so that's 0. And we're going to say that the hydronium ion concentration is negligible from the water. Now as the HA is added to water, part of it's going to dissociate. So we're going to lose some of that HA. We're going to lose some term, we're going to call that minus X. Well, when we lose HA, we'll produce 1A minus, and then we'll produce hydronium ions. This is based on the coefficients, remember, in our balanced chemical equation. So at equilibrium, the HA concentration is 0.012 minus X, the A minus concentration is X, and the hydronium concentration is X. Now if we write our equilibrium expression constant, or the mass action equation of our products over our reactants, because the A minus concentration and the hydronium concentration are the same, we're multiplying these together, so this becomes X squared. That's X squared over the reactants, so that's the concentration of the nicotinic acid, and remember the water is pure, so it does not show up in our equation. And they gave us the Ka value of 1.4 times 10 to the minus fifth as part of our knowns in the given information. Now we need to solve for X. So I'm going to multiply both sides by the 0.012 minus X and move the X squared to the other side. And we can use a quadratic formula to solve for X. And if you were to do the math for this, you get an X value of 4.0294 times 10 to the minus fourth. Now X is the concentration, remember, of our A minus and our hydronium concentration at equilibrium. And they wanted to know the pH of the solution. So if I know the concentration of our hydronium concentration at equilibrium, and that X is that 4.02 times 10 to the minus fourth, I can take the negative log of that value, and I put that in my calculator and I get a pH of 3.39. Now if I didn't want to use the quadratic formula to solve for this equation, I could also do an approximation. So remember we said if X is very small compared to the initial concentration, we can do an approximation. And so taking out a little bit from this 0.02 doesn't change the value that much, so we're going to approximate. So we get a value of 1.68 times 10 to the minus 7th when we multiply both sides by 0.012. And that equals to x squared. We take the square root of both sides, and we get an x value of 4.09 times 10 to the minus 4th. And if we plug this into our pH equation, we get pH equals negative log of the x plus. So see, either way we did this, the value came out to be the same. So this approximation was a valid approximation, and this saved us a lot of time rather than having to do the quadratic equation. So another example, what is the Ka? A 0.1 molar solution has a pH of 4.25. We first have to write our balanced equation, and they don't give us the name of the weak acids, we're just using an abbreviation HA. We set up our ice table. You initially have 0.1 molar HA and none of the A minus and none of the hydronium ions. Now they tell us that the solution has a pH of 4.25. So what I can do is use the relationship of the pH to find the hydronium concentration. So if I take 10 raised to the negative pH, I can find the hydronium concentration, which turns out to be 5.6 times 10 to the minus 5th. So if I know that's my equilibrium concentration of the hydronium ions, I can do algebra to figure out what the other values are from that change. So that means that the hydronium concentration had to increase by 0.5 times 10 to the minus 5th. And since we start off with no A minus, and this is a 1-to-1 mole ratio, we'll also have 5.6 times 10 to the minus 5th concentration of our A minus. And our change for the HA was minus 5.6 times 10 to the minus 5th. So if I take that 0.1 and subtract that amount of change, and I can plug that in here to find the concentration of our HA at equilibrium. I can then plug that into my mass action equation. So our Ka equals our products over our reactants. Now probably do an approximation here, but it's really not that much more work to put that in your calculator. So if you put that in your calculator, you should get a Ka value of 3.2 times 10 to the minus 8th. Another term when we're discussing acid and base is the percent ionization. And it's just another way to measure the strength of an acid by determining the percentage of acid molecules that ionize when dissolved in water. And so this is called the percent ionization. So the higher the percent ionization, the stronger the acid. And if we want to look at it in an equation, the percent ionization equals the molarity of the ionized acid, so what's already broken apart, over the initial molarity of the acid, times 100%. And since the ionized acid concentration at equilibrium equals the H plus concentration at equilibrium, the percent ionization can be written as the H plus concentration at equilibrium over the initial acid concentration times 100. So here we're looking at a problem where we're asked to calculate what's the 2.5 molar nitrous acid solution. So our first step is to write the reaction for the acid with the water. So we have the nitrous acid dissolving in the water to make the NO2 minus and the hydronium ion. Then we need to set up our ice table where we have our initial amounts in there, our change, and then our equilibrium concentrations. Now in this problem they didn't give us the Ka for this reaction. We'll have to look this up in a table. So if we look up the Ka value for the nitrous acid, we see that it's 4.6 times 10 to the minus 4th. So we're using that information as part of our mass action equation. So remember our products over our reactants. And because at equilibrium the NO2 minus concentration, the H3 plus concentration are the same, we can multiply those together. Those are actually squared, so that's x squared. And we're going to assume that x is a very small change. So we're going to say that basically at equilibrium the concentration of the nitrous acid is 2.5 molar. So I substitute in those values into our mass action equation. So the Ka was 4.6 times 10 to the minus 4th equals x squared over 2.5. Multiply both sides by 2.5 and then take the square root of both sides, and you get an x value of 3.4 times 10 to the minus 2nd. So remember, that's the concentration of our hydronium ion, and the concentration of our acid is 2.5 minus x. So the concentration, that 2.5 minus x, is 2.5 molar. So with sig figs, it doesn't really change. So we're just showing that the concentration here of the NO2 minus equals that of the hydronium. So both of those are that x value that we found, that 0.034 molar. So the percent ionization, remember, is the concentration of the hydronium ion over the initial concentration of the acid. So that 3.4 times 10 to the minus 2nd divided by the 2.5 molar times 100, which gives you a 1.4% ionization of the acid. So only 1.4% of that acid is actually ionized when it's dissolved in water. And again, because the percent ionization is less than 5%, that approximation that we did in the x value is small, so it's okay to do that approximation. Let's now discuss the relationship between the hydronium concentration at equilibrium versus the HA initial, so the initial acid concentration. Increasing the initial concentration of acid results in increased concentration of the hydronium ions at equilibrium. Increasing the initial concentration of acid results in decreased percent ionization. This means that the increase in the hydronium ion concentration is slower than the increase in acid concentration. So why doesn't the increase in hydronium ion keep up with the increase in HA? The reaction for the ionization of a weak acid is shown right here. And according to Le Chatelier's principle, if we reduce the concentration of all the aqueous components, the equilibrium should shift to the right to increase the total number of dissolved particles. We can reduce the aqueous concentrations by using a more dilute initial acid concentration. The result will be a larger hydronium concentration in the dilute solution compared to the initial acid concentration. This will result in a larger percent ionization. Now let's talk about how we find the pH of a mixture of acids. Contributions of the weaker acid to the hydronium ion concentration at equilibrium. For a mixture of a strong acid with a weak acid, the complete ionization of the strong acid provides more than enough hydronium ions to shift the weak acid equilibrium to the left so far that the weak acid's added hydronium concentration is negligible. For mixtures of weak acids, we generally only need to consider the stronger for the same reasons. And this is as long as one is significantly stronger than the other and their concentrations are similar, that we can make this assumption for when we have mixtures of weak acids. Let's look at finding the pH of a mixture of 0.15 molar HF, which is a weak acid, and 0.1 molar HClO2. So we're writing down the equilibrium reactions for each of the reactions involved. So HF combining with water to make the F minus in the hydronium ion, the hypochlorous acid dissociating its proton to form the ClO4 minus, and then the water, autoionization of water. The equilibrium constant for the HF is 3.5 times 10 to the minus 4th, and the hypochlorous acid has an equilibrium constant of 2.9 times 10 to the minus 8th. So the hydrofluoric acid is the strongest of the acids within this system here. So we're going to set up an ice table where we're looking at the HF dissociating, and initially we have 0.15 molar HF, no fluoride ions, and the hydronium ion concentration, we're going to say, is effectively 0. So we're going to lose some amount of X of the HF, that increase the fluoride concentration by X and the hydronium concentration by X. So then we find our equilibrium values. Now using the mass action equation for that reaction, the products over the reactants, we plug in our equilibrium values into our mass action equation. So this reduces down to x squared because the F minus and the H plus concentration are the same. And the Ka value, we can look that up. We said that was 3.5 times 10 to the minus fourth. And then the equilibrium concentration, the HF, we're going to say is 0.15 because we're going to ignore the x. We're going to make that approximation by saying that this x is negligible. Then I multiply both sides of the equation by the 1.5 times 10 to the minus 1 and take the square root of both sides, and I get an x value of 7.2 times 10 to the minus third. Then I compare that value of the x, the hydronium concentration, to the initial concentration of the HF times 100, and I get a 4.8%, which is less than 5, so it's okay to use this approximation that we used up here. So the F minus concentration, which equals the hydronium concentration, both of those values are 7.2 times 10 to the minus third when we solve for the x value. So if we want to know the pH is simply the log of the hydronium concentration. So we take the negative log of that 7.2 times 10 to the minus third, and we get a pH value of 2.14. And then if we want to just double check ourselves, so this is the nice thing about some of these equilibrium reactions. When you solve and find an answer, you can always plug in what you get and just double check to make sure that you did your math correctly. So we said the F minus was a 7.2 times 10 to the minus third, the hydronium was the same, and the HF was 0.15 minus x. Plug all that in, calculate the Ka, you get a value of 3.6 times 10 to the minus fourth, which is very close to what they gave us, so we can say that the approximation was okay, and within sig figs, we're good. So that ends our video for part 2. There's another video for part 3 for acids and bases. So that's what we've done here. We have a weak acid, if 100% ionization of it. Generally, we can ignore the contrast